All right, hello everyone. Super excited to be talking to you today about the future of human-centric explainable AI. And in this talk, I aim to convince you of two things. One, the current way, especially in education, healthcare, and human-centric fields, of doing explainability is broken. Post hoc explainers, which are the most popular kind, have serious problems, and there's no great or effective way to validate them. And the second point is that with interpretable-by-design neural networks, guaranteed interpretability does not have to come at the cost of performance or human understandability. So with that said, I'm Vinitra. I'm super excited to be here today. And I already had a great introduction, so I'll move on. But I wanted to thank both Professors Tanya Kaiser and Martin Yagi and their labs over at EPFL. So this talk, I'll start by talking about what is explainability, why we should care about it, what the current state of the field is, and why existing XAI methods are not enough. And finally, 3 ideas towards an explainable AI future, specifically in multimodality, using mixture of experts models, and using LLMs. So let's take a typical example in a human-centric field, in my favorite domain area, education. So there are students interacting with an online course, Coursera, edX, or the like, and they watch videos, they post on the forum, and we have these great interaction click streams, from which we can, of course, build a model to predict early in the course, let's say maybe within 3 weeks or 5 weeks of a 10-week course, whether a student is going to pass or fail at the end. And why we're interested in doing this is that specifically in online courses where teachers are not available, these kind of personalized insights are really helpful for students to learn effectively. But this why is kind of missing, right? Because the best models in these fields trade transparency for accuracy. And so identifying why is super important, both in education, but also in healthcare, for creating personalized interventions to get these struggling students back onto the correct learning path. And so we turn to explainable AI. Why is explainability important? 3 reasons that at least I can think of. There are many more. Building stakeholder trust in models. So when you see an explanation, students, teachers, parents, patients, doctors, they feel better about using this model. Secondly, auditing models when they make mistakes. And we've seen that they make a lot of mistakes. So being able to know when to intervene is an important contribution. And lastly, improving models with their own reasoning. And we saw an amazing example of this yesterday in Rich's talk with the model editing. Now, after talking to a lot of different teachers, students, etc., as well as reviewing a lot of literature, we've come up with 5 main reasons that you should consider in kind of deciding which kinds of explanations are relevant for your needs. So, using an explainer on top of an underlying model, if you use it multiple times, does the explanation come out to be the same? When it's inconsistent, we've actually found that people are really put off by this. Secondly, real time. Does that mean instantaneous, the next minute, the next lesson, by the end of the course? Accuracy. So can the model give an aspect of how confident it is in the explanation? Is it actionable? Are you able to take a next step based on the insight? And lastly, is it human interpretable? Is it easy for a non-data scientist to understand the explanation? And based on these, we kind of have this interpretability trajectory, right? There's intrinsic models, like these decision trees, which are very easy, because from the beginning, we already know exactly how every decision is made and why all the decisions are being made. We have in-hoc models, like, for example, gradient methods, where you're able to look at certain parts of the model weights to identify what is important in classifying this image. And again, what's important here is that you do need access to the model weights. And post hoc methods, for example, LIME or SHAP, where the model is a black box, and the explainer sits on top. And so we have global post hoc methods that are trying to identify how important is this feature to the prediction over all the cases, over the whole model, or local explainability methods, which we'll focus on a bit more, which deal with this student, this patient, this instance of a recommender system, or something like this. How do we explain why that prediction came to be? So now we'll talk about LIME. LIME is probably the most popular explainability method, just to build some intuition. And let's take our example of a student in an online course. So a student enters this black box model, and it's predicted that the student will fail. Now, how does a typical post-hoc explainer work? You can perturb the features for this student to get however many of X prime students that are similar to the original student in varying ways. And you can feed all of those X prime students into the model to get all of your Y primes, essentially all of the points that the student could have been, but has not been yet. And you can fit an interpretable model based on these X primes and Y prime students. So for example, a decision tree or an SVM or something like this gets fit on top of this interpretable model, and you can see exactly for this student why the prediction was made. Because if this feature was changed, it would have changed a different way, etc. Now, another very popular explainability method is called SHAP. SHAP tries to give a number, essentially a contribution of this feature to the prediction. How does that work? We have our student predicted to fail, unfortunately. And let's say we had 3 features that go into this model. Number of minutes watching the videos, number of problems this week, number of clicks on problems this week, and number of sessions overall. So what SHAP does is it looks at the power set, the coalition of these features. For example, a model where none of the features are included, 1 of the features are included, 2 of the features are included, etc. And you can see that already this is 2 to the 3 number of models, right? It gets expensive very fast. And what happens is that you train a model on each feature set in the coalition, and then you find the marginal contribution of a feature to the prediction. What does that mean? Let's look at F3, for example, feature 3. You take the difference between a model trained with F1 and F3 and a model trained with just F3, and you see the marginal contribution of F3 to this prediction, essentially the difference in the predictions between those models. But of course, that's not the only combination where F3 was added. It's also added in a lot of other cases, so you take the weighted sum of those contributions. But the nice thing about SHAP is that it's taking into account that F3 doesn't work just by itself. It works in combination with all of these other features and could have marginal contributions in that way. But you can imagine, this is super expensive, right? There are a couple of really nice optimization techniques, kernel SHAP, permutation SHAP, that make this process actually efficient to run, but it is still slow. And lastly, counterfactual explanations. Who of you has heard what a counterfactual is before? OK, some in the audience. So a counterfactual is basically you take a point and you generate a point with the smallest possible change that flips the prediction. So you have a student predicted to fail. What is the closest student to this student that would be predicted to pass? And you do these things through some nice technical techniques, but the advantage to this is very clear, right? You know exactly what you need to change to get onto the right trajectory. So what's the state of the art? The state of the art is basically that everyone kind of picks one of these explainability methods and many others and just implements them on top of their framework and says, this is what the model is doing, and it's great that we did explainability. Which is correct. It's great that they did explainability. But what we did was try to analyze, for the same models, for the same students across different courses, how do the explanations compare to each other? And probably the most important graphic from that paper is this one, where what you would expect to see is a cluster by symbol. So all the diamonds together, all the stars together, because they're the same students that went through the same model for the same predictions, so they should have the same explanations. But instead, you see clear clusters by explainability method. What this means? The choice of explainability method has a huge impact on what explanation you're going to get. Which means that picking any one of these at random can totally change what impact that you will have on interpreting your explanation. So, problem, these methods systematically disagree, and luckily this was also confirmed by a very nice paper from Harvard and MIT and some of the others. How can we build trust in them? Maybe we can turn to human experts, right? Because even if they all disagree, at least one of them could be more correct for at least our domain in education. So we talked to a lot of professors, terrible to schedule, by the way. Professors are very hard to get a hang of. And we conducted all of these semi-structured interviews, showing them multiple explainer results and having them validate which ones agreed with what they thought. So the study looks a bit like this. We picked a course pair that showed a difference in learning science behavior. So the same course offered as a hybrid course versus a completely online course, or the same course offered with more videos and less problems, or the other way around. And we showed professors 3 different kinds of explanations: LIME, SHAP, and then a confounder explanation that is supposed to be wrong, essentially the flipped version of a counterfactual. And what we found was quite interesting. What we found was this. All of these professors from around the globe had diverse prior perceptions of what enabled student success and failure, right? They all thought different things contributed. Makes sense? But this means that when they chose explanations, they often trusted explanations that aligned with their prior beliefs. So 50% of the time, they picked something that agreed with what they were thinking before, which means then they all disagreed. And in fact, they didn't even stay consistent between themselves. Only 3 of the professors picked the same courses, the same explanations as important for multiple courses in the pair. So, what can we take away from this? Explainability methods do not agree, and oftentimes in human-centric fields, human experts also don't agree on which explanations are right. So, where do we go from here? Interpretable-by-design neural nets. I think this is the direction forward for the field. I hope you also feel the same way. And I'm going to present 3 cool ideas of many out there about how to do interpretability by design for multimodality, for a mixture of experts, and discuss a bit the role of LLMs in this explainability space. So let's first talk about multimodality. This paper was a great contribution by multiple different labs. Super excited to have worked with these amazing faces over here. And let me tell you a little bit about it. So the premise of multimodality, as we've heard from a lot of these different conversations that have been happening at this conference itself, is that we can leverage the shared predictive potential of these different modalities together to predict well. And these deal with inputs with drastically varying sizes. But when you take all of these different modalities and you fuse them in parallel, you notice that this kind of limits interpretability. You can't exactly identify which modality contributed to the prediction. And it creates a dependency on modality availability. What do I mean by this? The current way of doing explainability, the current way of doing multimodality looks a bit like this. We have different inputs. We have the text inputs, we have image inputs, et cetera, and they are all mapped to encoders, which are all then added to the same encoding space, either concatenated or averaged or something like this, upon which they are decoded in a specific decoder task. However, especially in low resource settings, if a certain modality no longer exists, for example, chest x-rays don't exist in some certain low resource hospitals, this pattern that was already learned in the original data is now not there in the inference set and then is impacted when you're doing the predictions. Instead, we propose something that looks a little bit like this. So fusion in sequence. What do I mean by this? We have our different modular architectures that are fed to encoders, and this S that kind of represents, that is on the top left corner, represents state. So for example, is a vector that represents how a student learns or what the state of a patient is. And kind of like an RNN, you take, for example, a student that's in an online course, they've watched a certain video, and that interaction, what they watched, et cetera, is fed to an encoder with their previous state, which then updates their next state. And from this next state, you can decode on any number of tasks. And when you train all of these little modular architectures in parallel, you get interpretability for free. So evaluated on a number of real-world tasks, what we see is that performance mainly stays the same, both across single tasks and multiple tasks. But what's really cool is the interpretability. So you can identify at a global scale which modality was most important in creating the prediction. Or you can identify which modality caused the decision to flip. Or if you have a time series case, like the education example, you know exactly at which interaction, at which point the decision starts flipping and what actions can take to make it go back on the right track. And the other advantage is that it's robust to missingness. What do I mean by this? So when a modality is missing in training and a different modality is missing in test, which happens all the time in real-world settings, traditional multimodal architectures fail. They exhibit catastrophic forgetting. But multimodal, because it never sees those modalities that are missing, does not exhibit this problem. And therefore, it's really relevant in low-resource settings. And I'm super excited that one of the doctors who is working with us is starting a real-life clinical study based on this kind of model in low-resource settings for research purposes to associate and train doctors to collect all of this multimodal data, and especially because of these advantages in robustness to missingness and interpretability, these kind of models can be really useful beyond the lab in real life. Now, second idea, interpret CC. So this is all about a global mixture of experts model. Essentially, how many of you have heard before of the accuracy interpretability trade-off? A lot of people have heard of it. I'm trying to convince you that that's not true, but I think that it's not true because of sparsity. So take a look at this architecture. Let's say, with our typical example of predicting student performance, we have all of these different features that contribute to the student's performance. And for a specific student, we have a few layers that just decide which features are important to use for this student to be predicted. Maybe it can only be 2 features. Maybe it's only 1 feature. Maybe for a particularly hard student, it's 5 features. And in this way, you can feed only those features to the predictive model and get out output predictions. So in this way, you've only used these 2 features for this student, but maybe a different 2 features for another student, and you've kind of optimized both the accuracy and the interpretability through sparsity for certain human-centric cases. Now, the mixture of experts part comes into it like this. Let's say we can group these features into some semantically identifiable groups, either through LLMs or through a human expert. For example, all the features relating to videos, or features relating to students' regularity. And then only choose certain groups to activate, and only send the features relevant to those groups to these subnetworks that have become, in essence, experts at exactly those features together. And in this way, you can create a weighted sum of the subnetwork predictions and create outputs that are guaranteed to be correct, but do not compromise on accuracy if the network is trained appropriately. And the results are really good. They at least maintain or sometimes improve performance across a lot of these benchmark data sets. But importantly, these kind of explanations are preferred by teachers over other interpretable-by-design approaches. And lastly, illuminate. So this work we finished about 3 weeks ago, so it's super hot off the presses. And it's about how we can use LLMs in the explainability cycle. How can we do that? I don't think LLMs should act as explainers, right? Because we all know that they're kind of stochastic parrots. They will tell you what you want to hear. But LLMs could be really great as communicators of explanations. So let me show you what explanations often look like. This is a result of one of the explanations in some of the previous papers. 10 weeks, 45 features, 450 columns of feature values, hard for a student, teacher, et cetera, to digest. And you can post-process them into visualizations. And of course, we've heard from the data visualization people, so maybe this needed to be post-processed even further. But they're still really hard to understand. And this has gone through multiple iterations with a lot of different learning scientists, et cetera. So what if we could give all of that information in terms of feature values, importance scores, et cetera, all that context, directly to something that selects what's important in that explanation, packages it up nicely, and presents it to students or patients, et cetera. And this part is kind of an iceberg, right? It's very easy to say select what's important, but that in itself is an explanation. So how can we do this? We can turn to lessons from philosophy and social science theory, where people have created all of these ways of extracting explanations and use those as kind of concrete prompting strategies for LLMs to essentially re-extract something of a digestible or high-level explanation from these original explanation insights. So using Tim Miller's cognitive processes of explanation, we have causal connection, the explanation stage, explanation selection, and explanation presentation. So you can feed in your model prediction, your explanation, feature values, course context, all of this stuff, as well as a theory instruction, in this case, this is abnormal conditions, into a language model that then can generate text explanations, but these might still be too long for a student to digest. So you could use feedback theory from the learning sciences, as well as communication principles like Grice's maxims, to compress that further. And you get something that looks like this. So where am I going? Kind of a problem statement that's important in the educational feedback space. But how am I doing? This is really interesting, because it combines insights over multiple weeks, over multiple features, into kind of digestible insights. So in this case, indicates a need for maybe a more stable study environment, or your high competency in week 2 was excellent, but wasn't so consistent in other weeks. Maybe you're struggling with problem solving in week 5. And maybe you could preview upcoming materials. And therefore, some quick suggestions of what you could do next. You could try to, in the next week, try to build a solid understanding before you're attempting a quiz. Or you could revisit the previous week because it's going to help you on week 7. And you can also include a visualization, because we have these wonderful multimodal LLMs that can also write code and create plots. So from there, we talked to around 114 different students and presented them all of these different kinds of explanations of student behavior. And what we found is that over traditional explainers, this kind of LLM post-processing step makes it much easier to understand the insights. And especially the text part was more important than the visual part of the explanation. But the really cool thing is that students then selected an action to take based on their preferred explanation. And this action basically can be applied to a simulated next week for that original student's data. And what we saw, applying that across all of these different strategies, were that 2 strategies stood out the most. Again, all of the strategies improved their scores. So no matter what positive action students took, it improved their scores. But 2 of these strategies, especially contrastive explanations and necessity robustness, were really, really helpful in creating actionable insights. And so, the main takeaways, I think postdoc explainers have serious problems, and especially in human-centric fields, we should not be using them so much. But we could move forward in interpretable-by-design neural networks, where you could have guaranteed interpretability without having a cost of performance and having human understandability. Thank you very much.